Patty Simpson with Simpson Math. In this video, I'm going to introduce the normal distribution. So the normal distribution describes continuous variables. So we will be looking at variables that are continuous, like weight or height or length of arm span or fluid ounces, something that is a continuous variable. All normal distributions look like a symmetric bell-shaped curve. In a previous video, we went through and graphed a similar curve that is symmetric and bell-shaped. So in other words, all of our normal distributions are going to look something like this, where they have this bell-shaped curve that is symmetric. I could fold it right down the middle and they're going to the sides would match. The graph approaches a horizontal asymptote at y equals 0. In other words, this graph continues forever and ever, getting closer and closer to where y equals 0. It's a normal probability density function, and it's defined by this, this equation here. So our function is 1 over the square root of 2 pi, the standard deviation squared. All that's the square root of that, times e raised to the negative x minus mu squared over 2 standard deviation squared, or you could say the variance there. So it's a pretty complicated function there that we're looking at. This is also known as the Gaussian distribution. We call it the normal curve or the Gaussian distribution. And it is kind of a complicated formula or equation. Let's look at this equation a little bit closer. Notice that 2 is just a constant, it's just a number. Pi is just a constant, it's just a number, 3.14. E is just a number, 2.7-ish. That 2 is just a number, it's a constant. So, and this 2 is also just a constant. But there are a few variables in here. First of all, the standard deviation and the mean. So remember that this symbol means the standard deviation, and that changes from set of data to set of data. And then the mean of the data is that mu. And then the x is a specific variable that we are looking for. You know, that's our input, and then we get out our output that helps us to define this function. So, but this function is dependent upon those two factors, the mean and the standard deviation. So as we go through, that's going to be important, especially in the way that we notate things. The smaller the standard deviation, the skinnier the curve, and the larger the standard deviation, the flatter the curve. But no matter that shape, it will always have this bell-shaped look to it, where it's symmetric and bell-shaped. So maybe it is tall and skinny like this, or maybe it is short and flat like that. But either way, it's going to be symmetric, so I can cut it right in the middle and the two sides meet. And another really important characteristic is that no matter what shape it has, that it's still going to have a bell-shaped symmetric curve to it, and the area underneath there is going to be equal to 1, and that's going to be true whichever form it takes. So that's one of the characteristics of this function, is that the area underneath that curve will always be equal to 1. And we use this notation. This n tells me that it's a normal curve. And then we'll put in parentheses the mean, comma, the standard deviation. So if I write something like this in 18.1, that tells me that this is a normal curve with a mean of 18 and a standard deviation of 1. We're going to look in the next video. We'll actually draw a normal distribution with that mean and that standard deviation, and then we'll begin to look at the percentages or the area under the curve between certain values on the curve. But big deal, underneath the curve, the entire thing, the area always makes up 1. It's always this bell shaped curve that has symmetry, and it's reliant upon the mean and the standard deviation. Math Made Simple at Simpson Math. Thanks for watching.